There we go. Hello, everyone. Sorry for being a little bit late. I was having some trouble with the technology, but I am here. Today, we're going to talk about acid-base calculation practice problems, or we're going to walk through some. Before we do this, what I kind of wanted to walk through is our overall kind of how we're going to begin to think about approaching some acid-base problems. Calculations, yes, but also some concepts, because the concepts are going to help us with some of our calculations. So we're going to do just kind of a little bit of lecture at first. And if people have questions about concepts as I'm going through them, please feel free to go ahead and put those in the chat so that I can answer anything that doesn't make 100% sense. So what I want to do first is essentially introduce this idea that I call the p-scale. And it's not like something that I've made up. This is a true thing. But when we are learning about pH and pOH and pKa and pKb, they're kind of presented as separate concepts, but they're really not. So the p-scale is the specific scale that describes all of these p-values, and all it means when we're thinking about something on the p-scale is if we have some value x, this could be the H plus concentration or the Ka, fill in the blank. All the p-scale says is, hey, take the negative log of this thing. So, for example, when we think about pH, it's the negative log of the H plus concentration. If it's pOH, it's the negative log of the OH minus concentration. If it's pKa, it's the negative log of the Ka concentration. And if it's pKb, it's the negative log of the Kb. The reason that this is helpful is because a lot of people understand pH, and then they tell me that they don't understand things like pOH or pK or pKb, and I'm like, well, technically, if you understand pH, you should understand basically everything else, all of those other p-values. Why is this the case? Because if we recognize that the scale works the exact same way for each instance, then that should hold true regardless of what we're describing. So a lot of people would say, okay, if we're getting into the acidic side of things, a lot of people would say, oh, that's a low pH value, or we have a high H plus concentration. And if we were thinking about translating this over into something like pKa, because that also measures acids, then it's actually the exact same thing. So we have low pKa values and we have high Ka values corresponding to acidic stuff. And so then when we think about translating this over to the basic side of the scale, right? So if we replace this acidic piece, just erase this with basic, then if this is what we would normally state for what would lead to something being acidic, then all we have to do to essentially have the exact same thing hold true is change all of these values that stand in for acid things and simply replace them with the base component. So the pOH, low pOHs are basic, just like low pHs are acidic. So the lower your pOH goes, the more basic we get. Just as I was saying, like the lower your pH gets, the more acidic we get. And then the same thing is true with the hydroxide concentration, as well as not the pKa, but the pKb, as well as the Kb. So all of these things are essentially the exact same concepts. It's just a matter of recognizing that if you technically understand pH, and you understand all of the remaining ones as well. So this being the case, this means that if we want to make some conversions between things like pH and H plus concentration or hydroxide concentration and pOH, it's all the exact same math as well. That's kind of what we were describing previously. And before we go any further on this, what I want to go ahead and do is look at some just really basic conceptual questions on this idea so we can kind of just solidify what's going on here. So let's go ahead and switch over. We're going to look at some questions. Some of these are going to be really, really trivial. And that's purposeful. They're really, really trivial because the idea here is that we are going to see how this concept transfers over, starting with something that we do understand, hopefully that we understand, and transferring it over to something that maybe is a little bit fuzzier. So for example, we have this first question. It's fairly straightforward. A solution with which the following pH values is most acidic. So as we were describing before, right, lower pH values means increasing acidity. So presumably we just pick the answer with the lowest pH. That is 1. Okay. straightforward question, really not much going on here. When we begin to transfer to other scales, I want to keep this concept in mind here. So for example, this question is asking which of the following bases listed below is strongest. So let's think about how the pH worked. So we know that if we're looking for something that was, or we have a low pH, we said that that was the most or the highest acidity. And in this case, we're looking at bases. We're looking for something that is the strongest. So we can essentially sort of write this as most basic. And here we're looking at pKb values. So we basically just fill this exact same thing in because, as we were saying, those low p values, whatever they happen to mention, H plus here, is going to correspond to high in the acidity, or in this case, since we're measuring basicity on a p scale, lower pKbs are going to correspond with higher basicities. So looking through all of these answer choices, just like before when we were picking the most acidic solution, now that we're picking the most basic solution, it's the exact same thing. We look for the lowest value, which in this case is benzoate at 9.8. So hopefully this is helpful in seeing how these concepts are essentially identical, and we can see that they transfer over in terms of if you understand pH, you understand this as well. Let's go ahead and do a couple more so that we can kind of see this come full circle. So this one here is now asking about a solution that is the least acidic. So we've been talking about most acidic, but this is going to kind of hold true. And it's asking about H plus concentration. The corollary, just to put it out there before we answer this question with H plus, you're going to treat H plus and Ka values the same way, just like you would take pH and pKa values the same way. So what does this mean? If we're looking for something with the lowest acidity, so it's going to be the least acidic out of all of these, then we would look for something with the lowest H plus concentration, because acid is just how much H plus you have. We would look for the lowest number. Since these are 10 to the negative values, we look for the most negative exponent, which in this instance is going to be answer choice D. So let's go ahead and look at this next question, which is sort of flipping this script a little bit in terms of which direction we're looking, low versus high, but it's now asking about Ka. And remember, we just figured out how to do the H plus concentration, so now we're going to look at this for the Ka, but they work the same. So if we're looking for something that is the most acidic, so we're going to flip this arrow around, that would typically correspond to something with a high H plus. But because we can treat H plus and Ka identically, then what we're really looking for here is the highest Ka value. Whenever I'm tackling these Ka values and they give me all of the exponent values as well as the mantissa, that's just like a fancy word for that thing out front, that number out front, I always break this into two. I always look at my scientific notation first. So I'm going to evaluate these guys here. This is just so I don't get confused. And then after I've looked at this, I'm going to evaluate these numbers so long as my scientific notation is the same. So what do I mean by this? Okay, so first things first, I'm going to look for the largest Ka, the largest exponent. So we can get rid of the 10 to the negative 10 because that's really, really small in terms of factors of 10. Everything else is 10 to the negative 4, which essentially means that this is now irrelevant when we are considering everything else that's going on. We can just look at the numbers out front, and here this comparison is pretty easy to make. 7.2 is the highest, so nitrous acid must have the highest Ka value. Since it has the highest Ka value, it must be the most acidic. And again, we're treating it just like we would have if it was an H plus concentration. So hopefully this is all kind of making sense in terms of how it fits together. And then kind of seeing it all come together. There was a question, increased pK, decreased pKb equals increased basicity. Yes, and we are going to get to that concept next because they will not always give you the same matching pieces. So for example, here, right, we are asked for something that is the most acidic, but now we have a mismatch because we're given pOH values, which do not measure acidity, they measure basicity. So long as you know the trend, right, that if we were looking at low pH values, this would correspond to high acidity. If we carry that same trend over, but we look at this for pOH, right, we say pOH would equal high basicity, then we can just say, okay, that is going to be equal to low acidity because basicity and acidity are going to be opposites of one another, which means that we don't want a low pOH value. We instead want the highest pOH value that we could find, and that would be, in this case, answer choice D. If they were asking about pKa's and pKb's, not POH's and pH's, it's the exact same thing. So for example, we could substitute in a low pKb is going to be high basicity and then low acidity. And if it was asking for still the most acidic thing, then we would be, just like we looked for the highest pOH value, we would look for the highest pKb value. So basically, the way that we treat these is the same. We just need to make sure we're kind of paying attention to what it is that that thing measures. The pOH and the pKb measure bases. The pH and the pKa both measure acids. So long as we can kind of keep those two things straight, you really don't need to learn everything about each individual piece. You just need to learn the overarching concept and then figure out how to apply it in each instance that you're presented. Okay. All right, so there is one last question, and this is going to look at Kb values. So previously we were talking about things on that P scale. So now we're going to look at it if it was on the non-P scale, right? So that H plus, the OH minus, the Kb's, the Kas, and kind of go from there. Okay, so this says the conjugate acid of a base, which with the following Kb values would produce the most acidic solution. So again, we can just begin to think about how would H plus work, because that's the most straightforward. H plus, if it's high, that would yield an acidic solution. We can then replace this H plus with a high Ka value. And if we know that the Ka and Kb are inverses of one another, then we have our relationship that we care about right here, which is the most acidic solution will be the lowest Kb value. Now this makes sense to me because remember, this is looking at bases, and this is basically saying it is the least basic, which means that it also must be the most acidic, just because they're opposites of one another. So then here we're going to look for the smallest Kb value, which in this case would be the most negative exponent, and that in this instance would be answer choice D. So hopefully by now you can begin to see that these concepts are in essence all the same. And I think that this is really important because a lot of the MCAT is truly about concepts. Yes, we do need to memorize things. We do need to have some specific details down, but more often than not, we're going to be taking some overarching concept, recognizing that it applies in a lot of different circumstances, and then applying it to the question that happens to be in front of us. So hopefully this gives you a sense of how we're going about and doing this and gives you a good idea of basically our approach to specifically some of these more conceptual pieces that are part of the acid-base concepts. What I want to go ahead and do from here is move on to how we can actually begin to put numbers to this. How do we begin to connect the idea of pH and pOH and pKa and pKb and Kas and Kb's and how we can interconvert between all those different values and kind of keep all the different conversions straight. And to do this, what we're going to go over is what I call the acid-base concept map. I'll post a link to a much nicer version to an acid-base concept map probably in my channel at some point in time. But for now, I'm going to just kind of write it out. And what we're going to do first is we're going to just look at the pH, pOH, H plus concentration side, because again, because all of the math is the same, if you understand the side that we're going to look at first, which is the most typical one that people are used to, the pH and the pOH, you technically understand the other side as well. Okay, so what we're going to do is just think about the math that takes us from one place to another. So if we want to go from H plus to the pH value, we take the negative log of that H plus concentration. To undo a negative log, which is basically how you go in reverse from the pH over to the H plus concentration, this is where you take the negative pH of this value. And if we were to just essentially repeat this exact same thing for the pH and the pOH, we would see the exact same math again, and we're just changing what is getting put in there. How do we go between, say, these two pieces, though? How do we convert between pH and pOH and H plus and OH minus concentration? This is where that idea of like the KW, if you've seen like the value of 10 to the negative 14 or just straight up 14, that's where this comes in. And I'm not going to go into exactly why all of this makes sense because this is more about using this map than it is about any of the other pieces. So if we want to convert between H plus and OH minus concentration, so between concentrations or equilibriums, that's like your Ka, Kb, because remember those are equivalent. This is where they both, when multiplied, have to equal 10 to the negative 14. If we convert this into the log scale, right, that negative log scale, what is the negative log of 10 to the negative 14? That's just 14, which is why the pH and the POH have to add to 14. The reason that we shift from addition, to addition from multiplication is just has to do with how logs work. How do we use this? So it's a map, and a map is supposed to tell you how do I get from point A to point B. Basically, you would think about what you've been given. So let's say in this case, we're going to just put a big G over the H plus concentration, and we would think about where do I want to end? I'm going to put this in blue. So this is sort of what we have. We are given the H plus concentration. We want to end at the POH value. You then go and you're going to chart out how do I get from point A to point B. And my recommendation is that whenever possible, you take the P scale route. So go through the P values rather than trying to convert here. It's just a little bit easier in terms of the math. So for example, we would say, okay, well, the route I'm going to take is going to go through pH and then end up down at the POH value. So let's just go ahead and put some numbers to this, and then we'll look at some actual practice problems after I fill out the other side of this. Let's say that the H plus concentration, we'll do this in blue, put this down here, was equal to 10 to the negative 6. We would then convert this to a pH value. That's the first step that our map is showing us. This is 6. And then we're going to convert this to a POH value because this is the next thing in our step because that's where we want to end. These things have to equal 14, which means the POH must be, can't do math today, 8, not 12. There we go, 8. This is essentially how you use this map. This is usually the straightforward piece of the map. What I want to go ahead and look at is the other side. That is usually what gives people a little bit more trouble. But remember, as we've seen before, kind of everything that was holding true over on this left-hand side that we're seeing has converted really, really well and been equivalent to all of those Ka, Kb, pKa, pKa values. And that's the exact same thing that we're going to see here. We basically set up this chart in the exact same way, substituting in Ka and Kb for H plus and OH minus, and then pKa and pKb in these places here. All of the math is the exact same. So if we want to go here, it's the negative log. This is 10 to the negative pKa. To convert between these two, they have to equal 14. To get from, again, this side, this is 10 to the negative pKb. This is the negative log of that value. These guys are equal to 10 to the negative 14 when multiplied. So you can see that it's just the mirror version of this over on the other side. And since it's the mirror version on the other side, then so long as you have the left-hand side of the memorized, you technically have the right-hand side of this memorized as well. And so if we did the exact same setup as before, right? So we were given, this was like 10 to the negative 6, this was a pH of 6 and a POH of 8. If this was now just transferred over into, say, Ka, so the Ka is 10 to the negative 6, the pKa would be 6 and the pKb would be 8. So same exact calculations, same exact steps, it just happens to be on a different scale. So then you might wonder, why do we have a different scale? It doesn't seem that relevant. The big difference between these two is what they describe. So they're describing slightly different things. When we're talking about H plus concentration, what we're describing in that instance is the solution. So what does a specific solution that we're looking at actually have? And this is a little bit different than what's over here because this is really for your weak stuff because this is describing the equilibrium of if we have this theoretical reaction, what will we get once we reach equilibrium? Whereas on the left-hand side, we're just measuring a solution and we're saying, hey, this solution has 10 to the negative 5 molar H plus concentration. It's a little bit different than what's over here. But that means that we can actually convert from the equilibrium side over to the solution side using basically an equation that is an ice table just in equation form. I don't really like using ice tables, and that's kind of a whole other story, but I especially don't like using ice tables for acid-base stuff. The biggest reason being in this case is that you're never going to have stoichiometric coefficients, which is the only thing that like an ice table would maybe be helpful for. And so what you can memorize is that the Ka will be equal to x squared over the concentration of weak acid. And then the Kb over here is literally the exact same thing, except this pertains to base, as we've seen before. In this instance, x that will be equal to the H plus concentration. And then on the bottom, this x will be equal to the OH minus concentration. So again, we're seeing this parallel both on top and bottom, as well as to the left and to the right. And I realize that I'm a little off center, so let me just move this. There we go. Perfect. And so at this point in time, kind of what we're seeing here is essentially how we can begin to connect these two. So let's say that we made a really complicated problem. This is probably not something that you would see on your actual exam, but I want to show you just like how much you could use this. So let's say that you were given a pKb value. You were also given the weak acid, but they want you to end all the way over here at the pOH value. So again, what we're going to do, because it's just a map, is we go and we chart out that path that we would take that's going to take us through all of the things that we've been given. So the key thing here is because they've given us that weak acid concentration, we need to use that weak acid concentration. So we always take the pKa values or the p scale values whenever possible. We would come through here and then down to pOH. So this is essentially the path and the math that you're going to do. So let's just go ahead and again put some numbers to this. We'll put these numbers in red so they kind of stick out. So we'll say the pKb is, sure, let's make it 7. Sure. So pKa is then 7 because that would equal 14, which means that the Ka for this is 10 to the negative 7. Let's say that this Ka concentration, so that concentration of the weak acid is 10 molar. We just set this up and we're going to solve for x. So in this instance, let's see, move this here. Cool. We would have 10 to the negative 7 is equal to x squared over 10. We multiply both sides by 10. That cancels. This is going to be 10 to the negative 8. So if we take, 10 to the negative 6, there you go. The square root of 10 to the negative 6 is equal to 10 to the negative 3. The reason that is that anytime you take the square root of a 10 to the negative something value, you're just going to have that exponent. And now we have our H plus concentration because remember, x is equal to H plus. So this is now 10 to the negative 6. The pH is 6. Therefore, the pOH in this case is 8. So you can see that a question that maybe seemed really complicated, first of all, right? You're given pKb, you're given weak acid concentration, they want pOH. You're like, where the heck do I start? With this concept map actually becomes fairly straightforward, and it's just a matter of following through on the steps. So that's why I really like to teach my students this concept, because it takes these problems that seem like you need a lot of time, and then you can get through them really, really quickly. So now that I've dithered on about that for a while, let's go ahead and look at some questions on this. And we're going to go ahead and flip over to a different question set that I've made that is going to look at the actual p-scale calculations. And that's basically the application of these. So some of these we're going to go through really quickly because once you kind of get the hang of it, that's kind of how it should go. It should just be really quick. But anytime you're answering these questions, I always want you to double check that you don't have a mismatch between what you're given and what you're measuring. So what does that mean? So for example, here we are given, oops, that's not what I wanted. We are given the H plus concentration and we are asked for the pH. So these match. We can say that this is a match between the two. Since they match, we're not going to have to think about doing any additional steps. This is simply a negative log. If we take negative log of 10 to the negative 5, a log is like a exponent grabber. So the log portion just grabs this and returns this as a number. And then we take the negative of it, which is 5. So the correct answer here would be B. It's a pretty straightforward question, and we're going to kind of see them escalate as we kind of go through. Okay, so this is saying, what is the pKa of an acid with a Ka of 10 to the negative 2? So again, what we have to remember is that the pH calculation is the exact same calculation as calculating pKa or pKb from its corresponding value. So they match, right? It's Ka and pKa. All we need to do is take the negative log. So the log grabs the exponent. We take the negative of it. The answer to this is just 2. So it's just all the same math all the way down for all of these calculations so far. Okay, so what about this one? So this says if a solution has a hydroxide concentration, so let's just translate that. That's a OH minus concentration of 10 to the negative 11, then the pOH of that solution is, okay, again, we match, and at this point in time, hopefully you're getting the sense, we're just going to take the exponent with a flipped sign, so the answer to this is 11. All of these are pretty straightforward. Again, now we're going to go in reverse, right? So we've been calculating the negative log values, but now we're looking at the switching to the other side. So this is a solution with a pH of 5 would have an H plus concentration of, so we're going in reverse, but again, we match, right? We match. what have we been doing, or what's the calculation here? Well, if we remember from this little thing here, when we were going between these two, we were looking at the negative log, and how we undo a negative log is we take 10 to the negative of that p scale value. So we're basically just going to have 10 to the negative 5, and it's a match, so we don't need to do, again, any additional math. And as always, if people have questions or are moving too fast, please do let me know. Okay, so then what about this one here? This is another thing that I didn't mention, which is important to note. So this is, what is the pH of a 1 times 10 to the negative 6 molar HClO4 solution? So I was talking about how the H pluses and the pHs, they measure solutions. The other thing that they pertain to is strong acids. The reason they pertain to strong acids is because strong acids completely dissociate in solution. And so we can just essentially treat the concentration of a strong acid as the concentration of H plus or whatever it happens to be in solution. So in this case, we can go ahead and just replace that HClO4, because that is one of our strong acids, with H plus. And again, here, this is just a match of H and H. So this is going to be 6 because we just take the exponent and flip the sign. All right, what about this one? So what is the pOH of a 1 times 10 to the negative 1 molar LiOH solution? Okay, again, we don't have a mismatch. This is a strong one, so it just pertains. We're just going to flip this. This is 1. Okay, now we're doing the same thing, but we're just translating this into KBs. So we were dealing with pHs and pOHs before. Now we're going pKb to KB. It's literally the exact same thing all over again. So we would just do it 10 to the negative pKb. So that is 10 to the negative 4. All right, so here's now where we are going to see a mismatch, and this is where the acid-base concept map comes into play a little bit more. So for instance, here we're looking at hydroxide concentration. So we write that as OH, but here's our mismatch. So you want to make sure that you're always looking and identifying this mismatch. If people are getting these types of questions wrong, it's typically not because you don't know how to do this problem. It's because you didn't realize that they were asking for something other than pOH, which is normally what we calculate. And so in this case here, we want to take hydroxide to pH, not pOH. So they're measuring different things. So essentially what we'll do is we can just think about how this would chart out on our map. So we'll go ahead and just flip over to our map really quickly and sort of see where we're going. So we're going from the hydroxide concentration. So that hydroxide concentration, even though this is a little bit messy, is right here. And then we're going to go up and around. So we're going to go hydroxide, pOH to pH. So we'll go ahead and draw that out. So hydroxide to pOH to pH. And then we just think about the math that makes this happen. So this is just negative log, and then these two have to equal 14. So the hydroxide concentration is 10 to the negative 6, which means that the pOH is 6, which means the pH is 8. Okay, now we're working in reverse, right? So previously we had been looking at, given a concentration, what is that p-value? But now we're going to go and look at the other direction. So in this case here, it says a solution with pH 2 would have a hydroxide concentration of blank. So again, we can think about using our concept map, trying to use our recall. Just try and recall it now. So it's going to be pH. If we can, we always want to go through p scales. So we're going to go pOH and then to hydroxide concentration. So pH is 2, pOH is 12, hydroxide is 10 to the negative 12. Now we'll look at a couple more. So this is, what is the pH of a 1 times 10 to the negative 4 molar NaOH solution? So now we're going to combine ideas. So previously we talked about how this is essentially just going to be equal to a hydroxide concentration. So that's our first step. But we're stacking on top of this now. Okay, I need to go to pH. So we're going to be doing this math here. We've already technically done this, but it's kind of just recognizing that we have a strong base and that we need to take that next piece and convert it into just a hydroxide concentration. This is 4, so the pH would therefore end up being 10. Some of these are a little redundant, but I really want to make sure people kind of have this down, because what we can eventually do, and hopefully you're kind of seeing this, is that I'm starting to do these a little bit faster. I'm starting to skip some of those written steps. So let's go ahead and think about this one. Just trying to do it mentally. So this is, what is the pOH of a 1 times 10 to the negative 6 molar solution of HBr? So here's what I know. I know that this is a mismatch. So I'm going to need to do a conversion. I know that this is a strong acid, which is going to give me the H plus concentration. So that's going to be pH. The pH is 6. I need the pOH. They have to equal 14. That is going to give me a pOH of 8. So they can be this quick, and you don't need to necessarily write it out. Now, personally, on my exam, I would actually write this out just because I'm that person that's going to make that stupid math error. And so I always just will write it out for the sake of not making that mistake. But hopefully this is giving you a nice sense of how these different things kind of fit together and how we can begin to use this information in a way that makes our calculations on that kind of more basic side, not connecting the two pieces, much, much easier. So I want to throw this in here for completeness sake. It's probably not something that you're going to encounter on the MCAT, but people will often ask me, hey, Chris, how do we do the math on a log when it's non-standard? So everything that we've been dealing with is pretty standard so far. It's a 10 to the negative value. There's nothing out front. But what happens when we have something like this, right? The H plus concentration of a solution is 4 times 10 to the negative 4. What is the approximate pH of that solution? There's a little trick that if you want to memorize, you can. Do you need to know this trick? Probably not, but just in case, for completeness sake, let's go over it. So when you have log values, yes, you're going to grab the exponent. But if there happens to be an integer other than 1 out front, that is not technically going to give you the correct answer. But we can estimate this answer. It's not going to be 100% correct, as we're going to see here, but we can estimate it. And basically, the way this will work is if we translate this into the form of A, that's where that 4 is coming in, times 10 to the negative B, we can say, when I take the negative log of this, what will I do? So if we're going to get that p value out of this, the p value is going to be equal to, well, what did we normally do? We took the exponent and we just flipped the sign. So it's going to be the b minus, and then you just put 0.a. So in this case, the exponent, if we flip it, would be 4 minus, and this would be 0.4. So this is approximately a pH of 3.6, which A is as close as we're going to get, so it must be the correct answer here. As you can see, there's a little bit of a discrepancy. This is not going to give you a 100% correct answer, but it can help you if you're dealing with a non-standard calculation. So this is just kind of one example of how you would go about solving this type of problem here. Are there any questions at this point in time? I know I've moved through this stuff pretty quickly, but hopefully it's all making sense and it's kind of giving you a good idea of how it all fits together. I'm going to look out for questions while I prepare kind of our next piece. I'm just going to kind of be drawing it out and then I'll look at it. Will the video be uploaded for later reference? Yes, this video will be up for later reference. It will be posted, I believe, right away. YouTube kind of does it automatically, so I don't know how long it takes to go up, but it does go up pretty shortly after the actual recording is taken and the live stream ends. All right, so for our next concept, just while I'm kind of drawing this and looking for questions, we're going to go ahead and begin to discuss the idea of the log scale and how we can essentially use the log scale for calculations that are going to ask usually about how a change in that p scale is going to alter the underlying concentration, say the concentration of like H plus or the concentration of like a hydroxide concentration. Well, thank you. And kind of go from there. So what I want to do first is to get us kind of centered on this. Let's just kind of think about if we're looking at a pH scale, we'll say this is 7, 8, 9, 6, 5. We're going to go ahead and put what these would be for both the hydroxide concentration and the H plus concentration. So that is our H plus concentration. And then we're also going to look at hydroxide concentration. And again, we can just think about how these scales would end up going. So in this case, this would be 10 to the negative 9, 10 to the negative 8, 10 to the negative 7, 10 to the negative 6, 10 to the negative 5. Because remember, these have to multiply to 10 to the negative 14 because it's that H plus and OH minus concentration. And keep in mind, everything that I'm teaching you here, right, is on the pH scale. We're looking at the pH scale. But this would hold true for pOH, pKa, and pKb. So it's all the same. It does not matter which scale that we're talking about. So what happened, right? What happened to these concentrations as we moved from one place to another? So let's just kind of see, we add 1 to something on a P scale, how do our concentrations change? So if we're looking at the thing that this measures, this is the pH scale, we look at the H plus concentration, we should recognize that these are inverses. We've sort of seen that the whole time, right? As the H plus concentration goes up, the pH is going down. So if we increase the pH, we should expect the H plus concentration to decrease. And that's exactly what we see when we look at the H plus concentration. But it's interesting here because the H plus concentration is not changing by just +1. It is by 10 to the negative 1. Okay, cool. Now let's do in blue a bigger shift. Let's say we went from 5 all the way to 9. Well, what's the math here? Well, on this side, we added 4. And if we went from this would be going from 10 to the negative 5 all the way over to 10 to the negative 9, or that's a 10 to the 4 difference. And this is something that's going to be universally true, is that this unit change down here is going to tell you the magnitude, not the sign of the exponent, but the magnitude of the exponent difference between these two. And that's exactly what we're seeing. And to figure out whether it's a negative or a positive, all you're going to do here is think about it conceptually, right? I said that as the pH increases, then the H plus concentration is going down, which makes sense that it's a 10 to the negative 4 difference and a 10 to the negative 1 difference rather than 10 to the 4 and 10 to the 1, because that doesn't make sense. That's an increase. We needed it to decrease. But if we look at the OH minus concentration, which is this other one, right? We're seeing the exact same shift in overall factor, but the factor is going to have the opposite sign. So for instance, when we went from 5 to 6, if we look at hydroxide concentration, that's an increase by 10 to the 1. And then if we did the exact same transition and we're looking now at 5 to 9 and we're looking at hydroxide, that is a 10 to the 4 increase. So it's just a matter of looking at these two different pieces and beginning to kind of decide and make a kind of interpretation of what we're seeing based off of the concept. So we can use this to solve these log-based problems that I see a lot of people end up struggling with. And it turns out that even though this concept that I'm describing right now is in the context of pH, this works for a decibel scale as well. This also is going to work for any sort of log-based scale that the MCAT is likely to give you. Sometimes they might give you like the log of a cell count. That would be another example. So let's go ahead and look at some questions so that we can see how we actually apply these concepts. And for this, we're going to, again, look at P scale, just some logs here really quickly. So here we're seeing this pH increase, and then what factors does it change by? And I'm going to give you a little tip with this. So if you are dealing with a log scale, so say it doesn't really matter what it is, it could be decibel, it could be pH, it could just be a log. What you can do is essentially eliminate, if you're looking at that underlying value, so that H plus concentration, the thing that's not on the log scale, you can go through and eliminate anything that is not a multiple of 10. So for instance, how do we have a 2 times difference on a log scale? Well, you're going to have to move by non-whole units. That's kind of difficult math to do. Because it's difficult math to do, the MCAT doesn't ask you to do it. And so if you have to guess on a log-based scale question and you're looking at something like this, guess the numbers that are actually factors of, or sorry, not factors, but are multiples of 10. So we're really only dealing with either 100 or 1 over 100, and we'll talk about why these answers are correct in the first place. But let's go ahead and look at this question and see. So this is talking about what happens if the pH increases. So all we really have to remember is that as the pH goes up, the H plus will drop. If the H plus is going to drop in terms of factor, we have to have something that's going to make it go down. So it's going to be 1/100th of what we started with. It's going to be the fraction, since A would represent an increase in the H plus concentration, and that's really not what we're looking for. Now, how do we know the 100 is right, though? Well, remember what we had described before, where we were looking at the unit difference, and that ends up being our exponent. So this is going to be +2, which means that we're looking for 10 to the 2 of magnitude. But is it negative or is it positive? Well, it's a decrease in H+. That is going to be 10 to the negative 2. This is the exact same thing as 1 over 100. So this is essentially how you go about solving these particular problems. These usually give people a lot of trouble, but once you kind of get the hang of them, they're really easy, and I often feel like they're kind of free points. Let's go ahead and check, make sure I've coded this correctly, and look at our next question. All right, cool. So now we have this one here, and this is going to ask if the pOH decreases from 10 to 8, then the hydroxide concentration would change by what factor? So then we have these different ones. We have 10 to the 2, 10 to the negative 1, 10 to the negative 2, 10 to the 3. I always personally like to start with the conceptual piece first, but it doesn't really matter of like, are we going up or are we going down? So we have a pOH that's decreasing, which means that the hydroxide concentration needs to go up. So I don't want a negative value, which essentially means I can answer this question right away. A has to be right, but this also makes sense because this is a -2 or a 2-factor change, which means that we're looking at something that's going to be 10 to the 2 because we know that our exponent has to be positive. All right, let's go ahead and look at a couple more. So now we have this one. This says, if the pH decreases from 10 to 7, then the ratio of the original H plus to the new H plus is, so this is asking us a ratio, and it's going to look at the ratio of the H plus given some sort of pH change here. Again, we can walk through the exact same steps as before. As I scan through my answer choices, I'm getting rid of A and B because these don't make sense, right? They have to be multiples of 10. These are not multiples of 10. 3, not a multiple of 10. You can't multiply 10 by itself some number of times and get 3. So they're out. We want the ratio of the original, which is 10. So this is 10 to 7. When they say blank to blank, whatever they mention first is going to be the thing that comes first in this like colon piece. So this is basically saying original to new. So in this case, I would say, oh, okay, cool. So what I'm looking for, I just put it in terms of bigger, smaller, lower, high. Well, 10 in terms of H plus concentration is less acidic, so I would expect this to be a low number. And 7 is more acidic, so I would expect this to be a high number. I can use that to answer my question. This answer has to be C because it's the only one that gets the order of those numbers right. Now, 1000 also does make sense because as we can see here, there is a -3 difference, which means that there needs to be a 10 to the 3 difference between these or a 1000-fold difference because 10 to the 3 is just equal to 1000. So here you can see we're using the exact same concept. It's a slightly different question, but ultimately we don't need to do a bunch of complicated math. We can just use the concept of a log scale as well as knowing which direction our p-scale concepts are sort of taking us in. Make sure actually, cool. Okay, and now all of that has dealt with, you know, pHs and pOHs and hydroxides and H pluses. But again, because all those scales, as we saw before, are the same, I know I'm probably kind of repeating that a bunch, but I want to kind of just make that super clear, that we can use this exact same thing to begin to figure out how we have a Ka change given some sort of pKa difference. So here we're seeing that the pKa of an acid is decreased from 23 to 19. So we could think about how many factor changes is that. So that's going to be a difference of -4. And it says by what factor did the Ka of the acid change? So I'm just going to kind of think about this. So always, you can just plot this out. If you're ever confused, use the pH relationship to guide you. So we would say low pKa, that's like low pH, which is high Ka because that's like high H plus concentration. So if you're getting stuck, just go ahead and go back to pH. It'll help you kind of get it all clear. So we know that the Ka has to go up. So we don't want a 10 to the negative value. And since there was a 4-fold or a 4-unit difference, this has to be our exponent of 10 to the 4. So here we're seeing this for a pK or a Ka type conversion, but the exact same concept applies because the p scales are essentially the same. All right, let's go ahead and look at one last question, and then we will call it there. Hopefully this was helpful. And as always, again, keep putting questions if something's not making sense or you want any clarification. Okay, cool. So let's go ahead and look at this. So it says if pH decreases from 7 to 3, what is the ratio of the original hydroxide concentration to the new hydroxide concentration? So we have a mismatch. We need to pick up on that this is asking for not H plus, but original hydroxide to the new hydroxide concentration. Now remember, we don't need to convert this like we would for the other questions from pH to pOH to try and solve this, because if we flip back to our board here, remember how before, zoom out so we can see everything, what we can see is that these factors were the same, right? It was like 10 to the 4, 10 to the negative 4. It's just the sign that's going to be a little bit different. So let's go ahead and conceptually think about what would make sense. So we are decreasing the pH, and if we decrease the pH in this is what I know, decrease pH, increase H+, which will decrease the hydroxide concentration. So the new hydroxide concentration, when we lower the pH, this has to be the small number or the low number. And this must be the big or the high number. So that was going to help me eliminate any answer choices that don't have a large number first. So for example, these guys here, these don't make any sense. They are out. Now this is a matter of deciding between how many factors do I have of difference, right? Am I looking at 1,000? Am I looking at 10,000? Just think about the number of zeros. So this has 1, 2, 3, 4 zeros. So that would be a 4-unit change. 1, 2, 3. This would be a 3-unit change. How many units did we change going from 7 to 3? We changed 4 units. So we need to have a 4-0 difference between the two numbers, which means that the answer here would be B. So basically, the way that you work this is it's kind of the same steps as before, but we're working a lot more in the realm of conceptual understanding and then just thinking about how logs work rather than ever using some sort of equation that relates these two things. This was all I had planned for today. Now, since we do have a little bit of extra time, because I plan on these going to be around an hour, what I can go ahead and do is one of two things. We could talk about why you don't need the Henderson-Hasselbalch equation, or alternatively, we could open it up and people could ask any additional questions, kind of like a last week's content AMA about acid-base stuff. It doesn't matter to me one way or the other, but I'll go ahead and just kind of wait and see what people want, and then we'll make our decision kind of once I get some feedback and some comments from there. I don't see any comments so far, so what I'll go ahead and do is just do a really quick walkthrough of why we don't need the Henderson-Hasselbalch equation, and there is one comment in that, so we'll do that. So why don't we need the Henderson-Hasselbalch equation? Let's just look at the equation to figure out why we don't need it, which seems a little bit counterintuitive. So pH is equal to pKa plus the log of the concentration of A minus, that's the conjugate base, over HA, that is the acid. And this is going to tell us about the pH for buffer solutions. So why don't we need this? Well, this piece here is just going to be that log factor. So we can think about how many unit differences is going to equal the factor change, or the factor difference between these. And then we can also look at the pKa and the pH, and these are just scales. So this pKa is like a starting point, and then we take these concentrations and we're going to go and we're going to alter this based off of how the concentrations are going to be moderated. So for example, let's look at 3 different circumstances, and we'll walk through the steps of solving this, and we'll look at some actual problems with this as well. So let's say that we just have something and the pK is going to be equal to 6. So we have pK is 6, and then we're going to have a couple of different concentrations. So let's say that we have the concentration of A minus, and then we're going to have the concentration of HA, and I will just put out some different numbers. So this is going to be, this box is scenario 1, scenario 2, and lastly, scenario 3. So let's just say this is 1 molar and 1 molar, 0.1 molar and 1 molar, and 1 molar and 0.1 molar. Okay, so we said pK is our starting point. So our starting point here is 6. We then ask ourselves, more acid, more base. Because remember, if we go back and we look, the unit and the factor difference is going to alter us from our starting point. Well, if there's no difference between them, it doesn't mean that we favor either the acid or the base. If we don't favor the acid or the base, then we're not actually going to change anywhere, because if you don't have more acid than base, then you don't change your pH. So in this case here, the pH is just going to be equivalent to 6. Okay, that one's straightforward, and maybe it doesn't illustrate why we don't need this super well. So let's go ahead and look at this one here. The pKa is still 6. Remember, that's our starting point in all these situations. We now ask this question. We say more acid, more base. So this is more acid, right? The HA concentration is 1 molar, while the A minus, that's the base concentration, is only 0.1 molar. Well, what happens if a solution has more base or more acid? Well, it's going to get altered, and it's either going to go up or down in pH on the basis of what we have more of. In this instance, we have more acid, which means that the pH should go down. Well, but by how much? Okay, we're dealing with a log scale. And previously, we said that underlying thing that we're looking at, if it changes by a certain factor amount, then that corresponds to the unit amount. So long as we know how many factors are different between these two numbers, then we know how many units to move either up or down. So you can just see how many times do I need to move this decimal to get these things to be equal? It's 1 time, which means that we're going to go down 1, and the pH here would be 5. And sure, you could have plugged this in, but you don't really need to. Okay, that's great. What about this other one here? Well, this is the exact same thing. We have pK, we start at 6, and it is a 1 molar concentration, and we have a 0.1 molar of the acid. So we have more base in this case, which means that we're going to be going up instead of down. And again, it's only a 1 factor difference, so we're going to be adding 1, and so we would have a final pH of 7. So as I was saying, you don't really need to know the Henderson-Hasselbalch equation because we can essentially just use this every single time, and it keeps you from flipping. What I see a lot of people do is they will flip these two here, and they end up getting a number that is 1 less instead of 1 more, just because you flipped the two different pieces. And to me, it just makes a lot of conceptual sense that if you have a buffer that favors acid, well, it's going to be more acidic. Or if you have a buffer that favors base, it's going to be more acidic. So this is really why we don't need the Henderson-Hasselbalch equation, and it kind of then takes that concept that we were learning before, logs, and harnesses it and allows us to use the exact same concept multiple times, which is something I really like about the MCAT, because for the MCAT, there is a lot to memorize, and so anytime we can take a overarching concept and apply it to something else, then I really like that because it means that I sort of get more for the content that I have memorized. So let's just look at a couple of problems, and then we'll kind of call it here. And I'll answer this question that I see that has popped up. If you could go over optics. So I would be happy to go over optics. I actually have a poll that should be up right now, and you can vote on what you want July's topic to be. Optics, I believe, is listed. So if you guys want to see optics or any of the other topics that are listed there, make sure that you go and vote for the topic that's your favorite. I also have over there a vote for a strategy topic. So I have 3 things, not going to remember what exactly they are right now. But if you want to see one of the strategy topics, I think there's like cars and something else that's listed, then make sure that you vote on that post, and then you can go ahead and kind of guide what we do next. All right, let's go ahead and look at these, and we'll just kind of go through the steps. We'll just look at 2, and then we'll kind of call it from there, and hopefully this was helpful. Okay, so this says a buffered solution contains 0.2 molar of CHOOH with a pK of 3.7 and 0.002 molar of CHOO minus. What will be the pH of the buffer? Or what will the pH of the buffer be? Okay, so we're looking at a pH of a buffer situation. So we have pH, we have pK, we have some concentrations. This is essentially how you spot that it's a Henderson-Hasselbalch one. So remember, step number 1 is our starting point. Our starting point is the pK of 3.7. And then we ask ourselves, more acid, more base. So we need to be able to identify the acid and the base. This guy has 1 more hydrogen, so that has to be the acid. This is lacking that hydrogen, so this guy has to be the base form. So when I look at these 2, we have a lot more acid than base because it's 0.2 molar versus 0.002 molar, which tells me that I need to go down. So I can say, okay, I'm going to put a negative value right here. So I know I'm going down. Now I need to figure out how many am I going down. I will take my smaller number, move the decimal as many times as it takes to get to the point where it's equal. So that is 2 decimal points, which means I'm going to move 2 down. So this would be 1.7 as a final pH. So then the correct answer here has to be A, 1.7. All right, let's go ahead and do one more. Maybe not the flip of this, something different. Cool, let's go ahead and do this one. So this one is a little bit different in the sense that we are looking at not solving for the final pH, but instead we're going to be solving for the ratio of one thing to another. So acetic acid to acetate in this buffer. So we're looking at the concentrations and we're sort of solving backwards. This is still actually really easy. We follow the exact same steps, slightly different thing because we kind of know where we're going and we just sort of predicate and say, did we have more acid or did we have more base? And then by how many units do we differ? That's how many zeros we have to differ by. So starting point is pKa, that's 4.8. What happened here? We went up, right? So we have plus 2 to get to 6.8. Since it's plus, right, we're going up, it's more basic, so we're going to favor base. And it's by 2, which means that this will be a 10 to the 2 / -2 difference, or that's 100 difference. And then it's just a matter of ordering these two. Just like before, because we know that we're not dealing with because we are dealing with a log, we're not going to be looking at like 2s. These have to be multiples of 10s. And now we need to decide, is it 1 to 100 or 100 to 1? And then we just list it and see what do they want. They wanted acetic acid to acetate. So they want acid to base. We said it's going to favor base, so we need to have the base be high, the acid be low. So this should be 1 to 100, or answer choice B. So even if you're asked to solve for it in a slightly non-standard situation, this technique still works because we're basically doing the exact same thing. And it's just a matter of kind of following through the exact same steps. I said we would end on this one, but since I might as well show you the last way that they could ask this question while we're here. And in this one here, they actually don't give you the pK, which is normally our starting point. We do the exact same steps, but in this case, we're going to be working all the way backwards. So we'll still put in 1, but we're going to put a question mark. We put in 2. This is the pH. That's 3.4. And then we ask ourselves, did we favor acid? Did we favor base? So this says 0.5 molar acetic acid, 0.005 molar acetate. So we favor acid, which means that this had to be minus some value. Well, what is this minus? Again, we just figure out how many did we go down. So this is going to be a 1 factor difference. So this is 1. So what did this number have to be if we went down 1 from it? Well, it had to be 4.4. So the original pKa is 4.4. So this just shows you how we don't need the equation and how we can solve using this technique in 3 different ways. If they phrase this question in 3 different ways, it's still going to work. It's just a matter of continuing to go through the different steps and figure out, what am I missing? How do I solve for that particular piece? Hopefully this was helpful. And just kind of as a last piece, especially if anybody happens to be catching the tail end here, do make sure that if you are interested in seeing more of these and you want to guide next month's topic, that you pop over to the channel, look for the posts, and answer the poll that's going to kind of decide what we cover next. If I've not put a topic that you are really, really interested in and it's not on my radar, feel free to also kind of put a message in one of those polls as well and say, hey, Chris, I'd really like to see this topic. I'm open to suggestions. But other than that, that's all I have for today. I hope you all have a good rest of your night, and I look forward to seeing people in more live streams. Bye.